So just to give everybody a little bit of context, I have been studying reinforcement learning for it's getting close to 40 years now. And so this is a topic that means a lot to me. I've spent a good chunk of my adult life and some of my young life worrying about problems in this space. The last few years, however, I've actually been away from the classroom and a bit away from research, focusing on helping to support science funding in the U.S. and some collaborations with other countries as well. And so the talk that I'm going to give here is something that I worked on actually before I went into government. And so some of it might be a little bit dated, but I still think there's really important insights in here that that hopefully you'll find useful and interesting. If not because it's cutting edge, then at least because it's a little bit of snapshot of history. This is a moment in time in the progression of the field. All right, so let me start off by giving a little bit of information. Also, I haven't looked in this talk in a couple of years, so I apologize if I'm a little bit rusty. All right, so this particular piece of work came out of a project a collaborative project that I worked on with professors in a couple other schools, and professors and students in a couple other schools. And what we were trying to look into, what we were funded to actually look into was, okay, I heard a blunk blunk. I don't know what that means, but if that's like somebody putting a hand up or something, I can't actually see it. So just feel free to speak up. We were looking into the question of explainable reinforcement learning. So this is a moment in time where a number of studies, especially around deep Q networks or DQN, had come out showing that this combination of reinforcement learning algorithms with deep learning had actually produced some really remarkable successes, things that people had been interested in for many, many years, like playing Atari video games that I had worked on. In fact, arguably, I started that whole line of work. They were actually doing extremely well, way better than we thought was possible. And so what we wanted to understand is, okay, these learning algorithms are playing video games and they're getting very good at them. How are they doing what they're doing? What are they learning? And can we explain that? Can we provide an interface that would allow us to look into the networks themselves and get some kind of understanding of how they were solving the problem? So the question is, why does the DQN algorithm, the Deep Q Network algorithm, choose the moves that it does in Atari video games? All right, so that was the concrete problem that we're drilling down onto. But by the time we completed the project, we were not at all convinced that any explanation was possible, right? So we went from the algorithms are doing really well, they're solving problems well, to how can we understand what it is that they're doing, to maybe we can't actually understand what it is that they're doing. And the punchline, at least for me, is that the idea of Q values, which are so central to the way that many reinforcement learning algorithms, especially DQN, works, generalizing those Q values is actually very, very hard, right? So there's the way that when people solve problems and they act in the world, usually there's some sense that the thing that the person did in this situation would also apply to all these other situations as well. And the conclusion that I started to come to is the same is not true of Q values. So Q values are not really good at applying in one scenario and then generalizing to other scenarios and providing guidance in those. So let me walk you through how we got there. And hopefully along the way, you'll get a sense of why this is so difficult. All right, so what I'm going to do is start off with a detailed case study on one particular video game called Amidar, which, at least to me, I was not familiar with this game before. I actually spent a lot of time as a kid playing Atari video games, and we had a bunch of them, but we didn't have this one. So I hadn't seen this before. But it turns out that it's an awful lot like the game of Pac-Man, which was extremely popular back in the arcades in my youth. And I did actually play it on Atari as well. This is not that, but it's very similar to that. So just to introduce you to the game, if this is not a game that you've seen before, And again, if I could actually see your faces, I would know if you were conveying to me, "Oh, I have no idea what you're talking about," or "Yeah, yeah, yeah, we all know the game of Abadar." But let me describe the game anyway, since I can't really tell. So the actual player that is being controlled by the joystick is the yellow creature on the screen. So you can see it on the right center of the screen. It can travel along those purple lines, and as it does that, it kind of fills the track in. And what the player is trying to do is fill all the track on the screen in. All the purple lines stay static, but the yellow player visits all of those places. And once they're all visited, that screen is complete. There's a lot of points that are delivered, and a new screen appears. Now, that wouldn't be so hard, right? It's just kind of almost like a traveling salesman problem, except for there's those little purple critters in the upper left and the bottom left. And they move around on the grid. And if the player comes in contact with them, then the player loses a life. And once three lives are gone, the game is over, right? So no more points can be gathered after that point. All right. So the yellow player is trying to move around on the grid, visit all the places, and not hit the purple players. All right. So we took this video game. We turned the point values into actual rewards that the reinforcement learner can perceive and try to maximize. And then we trained it for a really long time, and it ultimately learned to play this game quite well. So if this video works, we should see what the player does, the trained player does, as it's moving around the grid. And you can see it's filling in parts of the grid. It's dodging and getting really close to the purple enemies, but actually missing them. As you can see, it kind of completing the board, visiting all the places that it needs to visit. It really looks like it's dodging quite well. All right, so it managed to get a lot of points there, which is great. This is another run, I think, which again, it does quite well. You can see it kind of approaching the enemies and then backing off, turning just in time to avoid them. It really looks like it's learned this game quite well. And so we wanted to understand how does it do this? What does it actually learned about this game? And how is it using that information to make such proficient decisions? This is, for what it's worth, this is way better than I can play the game, right? So I move around like that, and then I get surrounded by the enemies, and then I bump into an enemy, and then I don't fill in nearly as much of the board. So it does well. It doesn't do super well, as you can see. It hasn't completed the board. I don't know if it actually stopped or if we just stopped the video, but it's doing really well, but not. I mean, superhuman in the sense better than me, but not better than an expert. Human experts do much better in this game. All right, but it's still quite good. So there's something going on here. So how does it do it? How can we generate an explanation of the behavior that is learned by the reinforcement learning algorithm? So I wrote down, explain why explain matters. Why does it matter that we can explain the behavior of the agent? Well, for one thing, if we knew what it was doing, it would provide us with some kind of assurance that we could actually trust it to solve this problem. Now, of course, in a video game, we don't really need to trust it. It doesn't really matter. It's very, very rare that a video game player, somehow people's lives are on the line. But in general, the reason that we study reinforcement learning is because we think it's a really powerful technology for solving real world problems. And if we have reinforcement learners that learn about real world problems, we would like to know that we can trust them to solve these problems adequately and to not mess up and put people at risk. In addition, if we can actually explain how it's doing what it's doing, we might be able to suggest improvements, right? We might be able to notice places where the thing that it's doing could be made better. And that would allow us to make the agents that are learned better as well. So, okay, so that's why we care about explanation. What were we expecting to see when we dove in and we watched these videos and we're like, okay, this is really great. It looks like it's avoiding the enemies. It looks like it's seeking out unfilled lines that it can visit on the grid. We know that there's actually another aspect of the game that we know that it didn't learn about, which is it turns out if you've visited all four corners of the grid, it gives you superpower for a little while, and you can actually destroy the enemies. And then they reappear, but for a brief period of time, you're impervious to the enemies, which is great. There's no evidence that the agent, the reinforcement learner, learned about that and used that information to change its behavior. So we weren't expecting to see anything like that in our understanding of its policy. But we were wondering if it had learned things like evasive patterns, like particular moves that you can make in the grid that tend to thwart the enemies. And we also wondered if it learned priorities for filling in the board. Is it good to finish the lines in the corners first, or the center of the screen, and then work to the edges? Like, how did it actually go about it? This is a thing that if you play the game for a couple rounds, you start to feel like there's better and worse places to begin focusing. And so we were wondering if the reinforcement learner also learned that. So that's what we wanted to try to accomplish. That's what we were hoping to see. And finally, how were we going to go about doing this? So because this particular research group had spent a fair amount of time looking at the problem of causality, we believed that the only way to really get an accurate explanation and a meaningful explanation was to intervene and observe the result. Right. So it's the basic idea is, just like scientists, when they do experiments, they do controlled experiments. They change something in the world and they observe what happens as an effect. There's no way to make a real scientific theory without those kind of controlled interventions. We did the same thing with the agents. We put them in certain scenarios and watched how they responded, so that we can do what's known as counterfactual reasoning. We could ask, well, the thing that it's doing for this reason. And we know that's the reason, because if we take that reason away, it doesn't do it. So there's a whole philosophy behind this. I'm not going to get into it in this particular talk, but the notion of intervention, I think, is really essential to generating an explanation that is meaningful. All right. So we did some interventions. So what are some interventions? Let's see. Because this is a game that's actually represented in code, we can manipulate aspects of the code in various ways. So I think what's happening on the left here is, normally there are 5 enemies. We just got rid of one of the enemies. We just created a version of the game that was exactly like the original game, except one of the enemies wasn't there. And on the far right side, I think we eliminated all but one of the enemies. So there was 5. We asked the learn policy to behave in a world where there's only 4 of them. If you're a person, by the way, this is great, right? Like, whatever was happening before will still work, but now there's actually additional things that you can do. You can actually go to places of the grid that would have otherwise been occupied by an enemy that are now open. And that's even more true in the case of the grid on the right, where there's only one enemy. The game actually becomes quite easy. You can move around, barely having to worry at all about the enemy. And again, you put a person in this scenario, they actually do quite well. So let me see if I can show this video again on the left. All right, so watch what happens. This is now the same policy that was doing so well before. This is what happens when we take away one of the enemies. It just sits there and it gets killed. Right? Did you see that? I'm going to do it one more time. So it moved down a little bit, and then it just sits there, and then one of the enemies comes, and that's the end of the game. So instead of filling in, 2/3 or 3/4 of the grid, it actually fills in basically nothing, and then just sits there and waits for the game to end. Okay, so the grid on the right is what happens when there's just one player, and here it did dodge that one enemy, but then it went to the middle of the grid, and it is, I don't know, not to anthropomorphize too much, make it as if it were a person, but it's confused. And in fact, this is all that ever happens. The enemy continues to go around, and the player continues to just jitter in the center and not make any progress whatsoever. And again, people and reasonable policies don't behave this way. So what is going on? All right. So what we decided to do as a kind of a first step is we took a tool from the literature. This is from a 2017 paper called saliency plots. And what the basic idea of a saliency plot is, we ask the behavior of the agent, does it change if we actually hide from it different places in the visual field? So if there's parts of the grid that it can't see. So, okay, let me try this again. So we show it the grid, we let it make a move. Then we say, if we were to hide this part of the grid, would the move be the same? Where are the parts of the grid where, if we were to change what it can see there, its behavior would change most significantly? Those are the parts that are salient, right? Those are the parts, in a sense, that it's paying attention to, because its behavior actually is conditioned on what's happening in that part of the grid. If there's other parts of the grid where making modifications there or hiding that part of the grid doesn't have any change to the agent's behavior, we can assume that it's actually not. I'm going to sneeze. Hold on a second. Excuse me. Sorry. We can make we can come to the conclusion that it's not paying attention to those parts of the grid. And so what we do is we add color. We add a little bit of glow to the screen to show which parts of the grid really are having an influence on, first of all, the action that's chosen, and second of all, the value prediction, the Q value that the network is predicting. All right. And so what we found, okay, all right. So if you actually look at these grids, you can see which parts are glowing. The player itself is lit up on all these, which is good. Like, you'd think that a policy that's going to play this game should have some awareness of what's going on right around the player. So that's great. But the other thing that we can see, you can see it on the bottom left, and really easily the two grids on the far right. The score, right? The 6 on the right-hand side and the 0 on the left-hand side. The score is something that's paying really close attention to. And you wouldn't think that would be that important, right? With respect to deciding what action to take in the middle of a game. It's like, oh, I need to know, are there 13 points? Are there 11 points? Right? That's not the most, at least as a person playing the game, it's not the most relevant feature. And yet that does seem to be what the agent is paying attention to. If we actually blur out that score, then it changes how it behaves, and it changes how the values what values it predicts. So that was our first clue, right? That something, well, maybe our second clue, right? The first clue that something weird is going on is that when we made the game easier, it played worse. The second thing is when we asked what it is that it's paying attention to, we discovered that it was some irrelevant parts of the grid in addition to some relevant parts of the grid. So that's concerning. All right. Okay. Sorry. So there's an animation here as well. So you can actually see the player moving around. You can see the things that it's paying attention to. Again, the score is really salient. Like, it's paying a lot of attention to the score. And I think ultimately what we decided is the reason that it's paying such close attention to the score is because it learned a kind of dance, right? It learned a particular way of moving through the world that tended to do well. And the score was a very good indicator of where in the dance it currently was, right? So if you're going to learn a dance and you need to know what step to take next, it's really useful to know what part of the music is playing, right? And the score is kind of an indicator of how far into the game we are, and in a sense, how far into the dance the agent should be. Right. So again, it's sort of interesting, right? It's paying attention to the clock on the wall, right? Or the beats that have progressed, and less about the other dancers, less about what's in the world around it, which is actually a pretty sensible thing to do if you're a dancer. You don't want to be paying too close attention to the other dancers. You need to be doing the thing that's the right thing to do at that part in the song. But in a game like this, where you're actually trying to be reactive to the things around you, that seems like a very questionable kind of behavior. Now,
one quick question. Did you try to mask these scores and train from scratch and see what happens, whether it can learn again, or it's essential to have access to this information to make that dance happen?
That's a really great question. We did not do that study, but the paper that's referred to there by Gradius, Cole, Dodge, and Fern, they did exactly that kind of work in their study, and they found that, in fact, hiding the score from the player, certainly in the learned policy, that causes it to play badly. But hiding the score in the context of actually learning the game was helpful, right? It couldn't depend on that feature, so it found other features to pay attention to. So in classical machine learning, it feels like an instance of overfitting, that the system is able to use kind of irrelevant features to decide what to do. Mm-hmm. And if you hide those, it actually just forces it to do something that's maybe harder for the learner, but better for generalization.
Makes sense. Thank you.
Yeah, great question. Thank you so much. All right. All right. So that was in the context of Amidar. We had previously in my lab, we had done a kind of related study in the game. I think it was called Infinite Mario. So this is like the Mario video game where you're the player that's bouncing around in the middle there, and you can interact with the other things, which are enemies, but you have to hit them from above. If you hit them from below, then you lose a life. If you hit them from above, then the other player loses a life, or whatever, the enemy. And you can see it looks like it's playing this game actually really well. So this was a study that we had done, and we tried to train up various kinds of players to do well in this game. And again, it does seem to be doing really remarkably well. What I want to tell you, though, that's maybe interesting about this is it's playing with its eyes closed, right? The input to this particular, what you just observed, that particular way of playing the game, was it just played a series of joystick commands. It was not using the screen information at all. Because this particular game is deterministic, that the same sequence of actions will lead to the same results every time. And so the way that we did this, it was in the context, it was a different context, but seems really relevant, is that we would just randomly generate a sequence and then play it and score it. And just we kept doing that until we found something that scored well. So it was really just random search, right? It wasn't learning to play. It wasn't learning features, because all it was is just a randomized sequence of actions. And if we found a randomized sequence of actions that scored well, then we kept it. So this is a thing that happens in these video games. And this is a thing that I think we're seeing a reinforcement learning algorithm taking advantage of in Amidar. For what it's worth, before I go on to the next thing, for what it's worth, human players in classic video games like Pac-Man, humans also take advantage of that determinism. They often will learn or at least the experts, the players who played this game flawlessly, they actually learned a little dance. They learned a sequence of moves that was extremely successful. Now, they were smart people, and I think they had some hints about what kind of dances were going to work better than others. But at the end of the day, you can actually beat Pac-Man by executing a particular sequence of up, down, left, right moves. And people, if given enough time playing these video games, people will learn those. And so it's not completely different from what people do, but it is, again, not something that's easy to explain in retrospect, right? Like, why did you turn left at this moment instead of this other thing? Well, it works, right? It works as part of the sequence. There's really no other explanation than that, other than it just has a good outcome. So, and again, this is an example of that. Like, why did it jump on that enemy instead of this other enemy? I have no idea, right? This is a sequence that scored well. This is not, there's no kind of internal reasoning happening that's guiding its behavior, other than this is a sequence that worked well. Again, not necessarily a bad thing, but it is really frustrating to look at the behavior and try to improve the behavior without being able to explain it, without having any way of understanding it. All right, so we decided that we would take a step back and try to understand the process implicitly that we were taking for trying to assess learning, to try to measure how much learning was happening. And so we can think about this in the context of supervised learning as opposed to reinforcement learning, in part because it's just simpler, right? If we can understand the main concepts in the supervised learning setting, maybe we can transfer them over to reinforcement learning as opposed to generating them from scratch. So, all right, how do things work in supervised learning? In supervised learning, a learner is given a set of training examples, so inputs and then the corresponding outputs. And a lot of what these learning algorithms do is interpolation, which means that it's using the examples that it's received to make good predictions for other examples that are really from the same distribution. Extrapolation is the notion that we're going to actually be able to make predictions about things that are out of sample, that are very different from the examples that were observed during training. And so here's three different levels of of generalization that a learner might have. They're illustrated on this plot here. So the green dots are data points. The black curve is the actual function that we're trying to learn. And so if we ask the far left arrow, if we ask a learner, we expose them to the 5 green dots, and then we say, make a prediction about where the black curve is at a given location. The first one is we're asking it to make a prediction about a point that it actually already saw, right? And that's useful, right? It should be able to predict the right point for a point that it actually saw, but it's not a very strong notion of generalization. The second arrow, we're asking it to make a prediction between 2 of the points that it observed. And so that's really interpolation, right? Oh, I guess the bullets here, in the supervised learning, we're talking about 3 different levels of generalization. The first is making predictions on the training examples themselves. That's the first arrow. The second one is interpolation. We're between 2 points that were in the training set. And then the third one is extrapolation. We're actually looking outside the points in the training set. And we can apply these same 3 ideas in the context of reinforcement learning. So we did a little study, I guess, a little kind of thought experiment in a simpler setting than these video games, just a simple grid world. So this is the picture in the center there is a grid world where we're training an agent to move from S0 on the left to SG on the right. That's the goal. Right, and then we're going to ask, we're going to let the thing train for a while. Then we're going to ask it to make predictions in 3 different scenarios. One is on policy, which are the dark gray squares. These are the states that the agent visits as it moves on its learned policy from S0 to SG. Then there's the light gray squares, which are labeled off policy here. These are squares that it might have interacted with, or states that it might have interacted with during training, but it doesn't actually visit them anymore once the policy is learned. And then the white squares are unreachable states. These are states that we could put the agent in those states, but the agent can't reach those states starting from S0 on its way to SG, right? In particular, I should probably say the actions in this particular environment are just up and down. On every step, the agent moves 1 square to the right, and then either up or down or staying in place, depending on the action that's chosen. And so the white squares there's no way starting from S0 to get to the white squares, right? So in the upper left, it can't get there because it's moving to the right. And even if it goes up as fast as it can't visit the squares in the upper left. Same thing with the lower left. And the red squares are actually an obstacle. And so all the white squares that are kind of in the shadow, as it were, of the red squares are also unreachable. All right. And so if we were to train up just a standard Q learner on this environment, we'd expect it to have really good information about the dark gray squares, because those are the ones that it visited a lot during training. Maybe some information about the light gray squares. These are squares that it might have visited during the training process. And really no information at all about the white squares, which it can never, ever visit. So, all right, so we did that. We trained an agent, and then let's see what we're saying on this slide. All right, so yeah, sorry, I probably should have taken a look at this slide in advance. Let me think about what this is saying. Synthetic agents, separately trained built agents used to produce states, human agents. All right, well, so I think what I'm trying to get at on this slide is the notion of there's lots of different ways that we could do the training and that we could do the evaluation that take advantage of kind of different ways of intervening in the environment. And so one thing we could do is consider states that are off policy, which is to say they're not visited as the agent moves from the initial state to the goal. But with K off policy actions in sequence, it could actually get to such a state, right? So these are things that we can let the agent behave, it can move around in the environment, and then we intervene and we say, okay, we're going to force you to take K, let's say K is 3. We're going to force you to take 3 actions that are different from what you would have taken following the policy. And then we'll see, states that we visit in that scenario. We could also, we could look at states that are visited by people playing this game. We could consider states that are visited by synthetic agents. So sort of other reinforcement learning agents that are trained or built differently to try to access different states. And we can look at states that really are unreachable, that we'd have to kind of force the agent to start someplace different. Right. And so I see. Right. So these are things that we could apply to that grid rule example, but we can do very similar sorts of things in Amidar to get a sense of how the learned policy behaves in special states, right? States that can be reached in other ways than just the states that the agent reaches kind of on its own. All right. And so given those kinds of various setups, we have 2 different evaluation metrics that we focused on. One is called value estimation error, which is to say, take a look at the Q values that are being produced by the network internally, and then we can actually run the policy and see what value is actually attained from that same state action pair, right? So a Q value in reinforcement learning is a prediction of how much reward do we expect the agent to receive if it's in that state and takes this action and then behaves optimally after that. And so we can ask, how well does the agent actually predict those values for states generally, not just states that it visits along its policy, its learned policy. So that's one metric. Another metric is total accumulated reward. How much value does the agent actually get? So what we want to argue is it's not enough to just do well, which is to say have high total accumulated reward, if it's for the wrong reason, right? If it's taking an action that isn't really justified, that is to say, it's taking that action because of particular Q values, and those Q values are wrong, right? If that's the case, then we shouldn't really believe that, yes, it's doing well, but it's not doing well for any kind of well-justified reason, right? Because the reason that it took that action is because the Q value suggested it, but the Q values are just wrong. So if it's doing well, it might just be getting lucky. And you can't really explain luck, right? You can't really explain, well, why did it do that thing? Well, because it just did that thing. There's no deeper justification than just it's the thing that it does. All right. And it's not enough to know what you will do if it's bad, right? So it's also bad if the agent has low V, which is to say low value estimation error. It actually is accurate at predicting values, but it gets terrible total accumulated reward, right? So high TAR, high V is bad, right? High reward, but high value prediction error is bad because it's doing the right thing for the wrong reason. And low value estimation error and low reward is also bad because it's actually just doing the wrong thing. And so what we wanted to do is look at what can we learn about the total accumulated reward and the value estimation error with all kinds of different ways that we can intervene on the policy, right? Just forcing it to visit other states. All right. And so what do we see? All right. So C is the control. So if we take the policy and we test it on the states that it actually visits in whatever it is that it learns, what we see, that black bar there, is that it has high TAR and low V. So it's actually doing well and it's predicting good values. So that's great, right? That's on the states that it actually visits on its learned policy, it really is doing the right thing. We can also look at what happens if we force it to take 10 off-policy actions, and it still does actually pretty well. At 20 off-policy actions, it starts to dip a little bit. It doesn't play the game as well, and it doesn't predict as well. But once we start to take more dramatic interventions, the performance really starts to fall apart. So if instead of starting it where the agent wants to start, or kind of where the game tends to start, we actually allow a different agent to control the game for a little while and then switch it over to the new agent. Or we let a person control it for a little while and then we switch it over to the learned agent. And what we see there is that it has both bad value, sort of moderate value estimation error. It's not as good at predicting values, and the rewards that it's getting are actually quite bad in both human starts and agent starts. In addition, and that's in terms of interpolation. So these are states that are visited during a game. We can also look at extrapolation, where we're forcing it to look at states that are not visited during a game, maybe not even visitable during a game, because we've actually intervened and done things to the game that can't actually happen during learning, which again, people handle really, really well, but these agents handle quite badly. If we add a line segment filled in before the agent actually starts playing, so make the game easier, that's ALS, we can see that it's the amount of reward that the agent gets drops. If we remove an enemy, ER, that's the blue bar, the ability of the agent to get high reward drops, and its ability to predict starts to go bad. If we shift the enemies, we kind of move them around a little bit, that also is bad. If we pre-fill in line segments, so we partly solve the game on behalf of the agent, performance completely tanks. It doesn't know what to do with that information. And if we start the player from some kind of random board position in terms of what's filled in and where it starts, it's just terrible. It can't actually play the game at all. One thing that we did find is across all these different evaluation scenarios that we used, that the value estimation error and the reward tended to correlate. So basically, a thing that's bad for predicting one tends to be bad for predicting the other as well. And right. So then we did an experiment where we tried to say, okay, well, so it is playing okay. So something good is happening. What can we say about the Euclidean distance of the states that are visited versus the compared to the distance of the states that are visited to the states that were visited during training. All right. So we actually during the training process, we just made a big database of all the different states that were visited. And then after training had taken place, we asked how near are the points that we're asking it to make predictions on to the states that were actually visited during the training process. And we did that again for the control scenario and for the enemy removed and the enemy shift. And what we found is that the learned representation, the stuff that the way that the activations work inside the network, the deep network, does not find the novel states to be like those seen in training. So the states that we put the agent in and ask it to make a prediction, they just are very weird, unfamiliar states to the network, right? That the activation patterns that are caused by those new states are very different from anything that it encounters during training. And so the worse off, so kind of the more foreign those states are, the more we see this Euclidean distance to the nearest training instance to be high, right? In the control condition, the black curve, most of the points are really close to things that it has seen. But in, for example, the FLS and the PRS settings, the training points, the encountered points, the test points are really far from anything that it's ever seen. So all this is really saying is that the algorithm is doing a terrible job, or sorry, that's a little unfair. It is not generalizing well. It's just not, right? That unfamiliar states are unfamiliar, and there's bad predictions happening on them. Conversely, states that are very familiar, states that it's seen many, many times, states that it knows how to deal with, the predictions are actually quite accurate. But what we'd expect these learning algorithms to pick up is an ability to really understand the game much more generally and much more thoroughly than what we're seeing. Instead, what we're seeing is if it's a state that it's been to before, it makes pretty good predictions. If it's a state that it's not been to before, it doesn't make very good predictions. And that's pretty weak as far as generalization is concerned. So it can play the game, but it's really only limited to playing well in states that it has experienced, usually often. Okay. All right. So if that's the scenario we're in, that we have these learning algorithms that can actually do well in practice, but they seem to do really badly if you kind of push them outside their region of familiarity. What can we do to actually make generalization better for these agents? So we did a couple different things. Some are kind of more motivated by the supervised learning literature. Some are more motivated by the reinforcement learning literature. But one of the things that is true in supervised learning, it was true when this talk was written, but I think people are even more aware of how true it is now, that a lot of these algorithms are just very data hungry. The more data you give them, the more they can actually use that to generalize. So let's try that. Let's actually try giving the learners more data. Let's try doing regularization, right? Making the model simpler, the network smaller, so that it's forced to generalize, right? That it's forced to do something meaningful with less representational resource. And again, these are tricks that we know from the supervised learning world, maybe less so the deep learning world, but the second one. But in general, this is a standard thing. If you want, if you're experiencing something like overfitting, where the model is making good predictions on things that it's seen and bad predictions on things that it hasn't seen, simplifying the model can actually help with that. In the reinforcement learning setting, we can think about increasing the data by increasing training time. So just like running more. Okay, so how can we get more data? How can we do simpler model regularization? One way in the reinforcement learning setting is just train it longer, right? Just let it get more experience to things. However, another idea is that could actually lead to it just learning the same states more because it's spending more time in states that it's actually visiting. So we can also force it during training to visit a more diverse set of states. We can diversify training by randomly starting it in different places in the environment. And of course, we can also reduce model capacity. We can actually take the neural network and just make it smaller so that it can't memorize as well. All right. So what happens when we actually do that in the context of Amidar? So giving it more training data actually makes things worse. Well, in particular, if we give it more training data by just letting it run longer, then what it ends up doing is just getting more and more and more experience with the small number of states that it visits once it's learned a pattern that seems to work. And so that actually causes it to overfit even more dramatically. So how is that shown in the figure here? Let's see. Right. Okay. All right. So right. So each of the lines, this is the far left plot. So 1, 2, and 3 correspond to the left plot, the middle plot, and the right plot. So the first plot on the far left, what we're showing here is 1, 2, 3, 4, 5, 6 different ways of assessing the algorithm's abilities or knowledge, right? The control one is with respect to just really visiting the states. Yeah, okay. We're measuring the performance, in particular here, the amount of reward that's obtained from states that it visits along the way, like states that it visits by following the optimal policy. That's the black line. In the blue line, on the other hand, is what happens if we remove some enemies. So we train it up, and then we ask it to make predictions, and we ask it to perform in states that have fewer enemies than the actual game. And so what we're varying on the x-axis there is the number of training steps. How much experience does the agent have? And then what we're measuring on the y-axis is, okay, the resulting, the policy, the Q network that results from that, how is it doing? And the fact that what we're seeing in like the blue line is relatively flat, it's going up a little bit. The yellow, the red, the purple lines are relatively flat, but the green and the black lines are going up. Well, and let's focus on the black line in particular. More training means that it's actually doing better. It's getting more reward from the states that it actually visits in that learned policy. But the fact that it's not doing any better on other states means that it is memorizing, it's overfitting. It's actually getting better and better at those states at the expense of, or at least without improving other states. All right, so that's what we're seeing on the far left. To just training it more kind of gets it even deeper into the groove, right? It's getting more and more experience with the things that it already has experience with, and correspondingly less and less on the things that it doesn't have experience with. All right. 2, the middle plot, diversifying training experience helps a bit. So we looked at not exploring starts, basically always starting from just the empty board. That's on the far left. And then we also looked at 30 exploring starts and 50 exploring starts. That means we're going to take 30 random actions or 50 random actions just to get the agent up and running, and then it's regular learning from there on in. And what you can see is that in almost all the cases, it's better to have the 50 initial exploring actions than to have no exploring actions. Right? So you can see a little bit of positive slope on these lines. It does seem to improve things to have some amount of diversity in the initial states. All right, and then the third plot.
A quick question.
Yes, thanks.
So what exploration strategy did you use in the algorithm?
Right, so during the actual algorithm itself, I think it was just a mild kind of epsilon greedy. So it tended to just take the actions that the Q values told it to take, but maybe with a little bit of extra randomness during the actual training process. Here, for the exploring starts, it's taking a whole bunch of random actions just to get going. But then during the actual training process, it's taking I think a very small number of random actions. We follow whatever was done in the original DQN paper from DeepMind.
I see. And didn't you try any other more complicated exploration strategies, see what happens? Because we see in the middle plot that exploration seems to help a lot or help moderately in certain cases.
Yeah, no, it's a really good point. We did not, this particular effort wasn't focused on exploration per se. I think at the time there was a lot less, I think, of an understanding of how to do good exploration in these deep networks. But you're right. There's now a lot of really good algorithms out there. We should kind of revisit that. Thanks. I don't know if anybody listening wants to do some experiments like that, but it does seem like a good idea.
Great, thanks.
All right, and then finally, the last bit we looked. Okay, so what TLHC 256HU? I don't remember what those mean anymore. But we're modifying the. I think 256HU is 256 hidden units. So we modified the structure of the networks that we were training. HC. I'm not remembering what TL and HC are, but the thing that we got out of this anyway is that sometimes reducing the model capacity seemed to help, and sometimes it seemed to hurt. It just wasn't really clear what was going on. So that was mixed. All right, so that's all I'm going to say about Amidar. One of the things that my group did kind of after that work was to say, what is it that you can generalize, right? The Q values seem to generalize really relatively badly. But a lot of these games, the dynamics of the game, right? Sort of the world model is what is consistent, right? When you move the joystick up, that has a very consistent and easily described effect. So we thought maybe the issue was that DQN was never going to be a good idea for this. DQN is never going to generalize well for these kinds of games. Instead, we should look at other ways of doing reinforcement learning, right? And there's really kind of 3 main flavors of reinforcement learning. There's reinforcement learning algorithms that focus on learning values, like DQN. There's reinforcement learning algorithms that focus on learning policies, like policy gradient type algorithms, of which, those have really been the most successful in the deep learning world. But then there's also model-based reinforcement learning algorithms that use their generalization capability to learn a model, and then that model is used to plan out actions in the world. And so our impression was, well, for these kinds of environments, you'd really expect the model to generalize most effectively. Now, of course, the issue with model-based learning is that you can learn a really accurate model, but you still have to use it to decide what to do. And these models tend to have to be really accurate to be able to do that well. And it's also extremely expensive to use the models in that way. So that's a caveat. But oh, it says last week. It is definitely not last week anymore. It was last week when I first put these slides together. Sorry. All right, so we decided we would do an experiment with an environment called Coin Run that we particularly liked. Unlike Amadar, we have the ability to run this environment in ways where the environment itself is somewhat randomly generated. So there's consistent dynamics, but like the details of maybe the background or exactly the arrangement of the enemies and the obstacles change. And for the same reason that was being pointed out, like exploration is a good thing, forcing it to experience lots of different environments actually is a good thing as well. If you really want generalization, if you wanted to understand how to do a whole bunch of things. All right, so we took the methodology and platform from a 2019 paper, and these little mini video games. These are not games I think that people really play, but they're video game like. And they're about collecting a single coin at the end of the level. So let's see if we can picture this. So take a look at the bottom left corner. There's a little space creature. That's the agent. That's the player. Then there's a step up. There's an obstacle. And then on the far right, towards the middle, there's like a glowing yellow circle. That's the coin. That's the target. It's trying to get to that as quickly as possible. We looked at three. So again, the game engine is set up to generate lots of challenges in this space. So instead of just like in the Amadar case, seeing the same exact setup over and over again, where it can deterministically play it, instead, each time that it's asked to play the game, some stuff is randomized. The position of the step, the position of the obstacles, the background colors, and so forth. So the hope is it'll learn to ignore that stuff because it's not really relevant across games, even though that may be relevant within a game. So we looked at one difficulty level where all the games that are generated were very small, like in the bottom left there. Level 2, they are bigger, and also there are, I don't know if you can see them, but there's like little saw blades, little circular saw blades that if you bump into them, then you lose a life. That wasn't true in the first one. I don't think there was any obstacles that were deadly like that. And then the third level of difficulty on the far right here, much bigger, lots of things that can actually cost the agent a life, and so on. All right, so the agent spawns in the far left, the coin is on the far right, it has to get there as quickly as possible. There's obstacles, enemies. The level ends when the agent bumps into something bad, or if 1,000 steps progress and it can't get to the goal. Okay, all right, so this is a much sort of richer space, and again, you have to generalize to be able to play in this game, right? Because each time a level is shown to the agent, it's different than any level that it's ever seen before. So we thought, okay, we're going to definitely see generalization here. All right, so what I'm showing on this slide are actually results from the Coin Run paper, where they looked at, let's see, they looked at two networks. They looked at PPO, which is a policy optimization algorithm. They didn't report results for TQN. So all the results that they did was with the policy search approach. All right, percent levels solved. Training test, number of training levels. All right, so great. Okay, so here's the setup here. We're going to, in fact, not generate a new training level every time the agent is interacting with the environment. Instead, we're going to create a training set of a bunch of levels and different size collections. So all the way from 10 squared, which is 100, all the way up to 10 to the fourth, a little beyond 10 to the fourth, which is 10,000. And what we're gonna do is each point on this plot, let's look at the far left plot. Each point on this plot is we generated a training set out of using this random level generator, we generate a training set of a certain size. Then we train and train and train and train on that set of environments until the agent is all trained up. So when we're done running reinforcement learning, and then we test the policy that's learned on those same training levels and newly generated training levels. So the blue line represents how well the agent plays on environments or levels from its training set versus how well it does on the red line is how well it does on newly generated environments. And this kind of, I don't know, what does it look like? Like a greater than symbol, right? It's wide at one end and narrow in the other. That's exactly what overfitting looks like, right? This sort of notion that as you move to the right, we're using more training data and the two lines are coming close together. Once they meet, that's like perfect generalization, which is to say there's no particular advantage for the algorithm to run on a training example versus a testing example, a new example that it's never seen before. That is truly its ability to generalize. But on the far left, what we're seeing is a huge gap. We're seeing overfitting. We're seeing the agent is trained on 100 environments and it learns those 100 environments actually really, really well. But it does extremely poorly on environments that come from the general distribution that it wasn't trained on. Right. So this is a good plot. Like this is the sort of plot that you'd expect to see. On the far left is overfitting. On the far right is actual successful generalization. So I'm not sure what the dotted line is. Does it say? I don't think it says here. All right. So the plot on the left is PPO, policy gradient algorithm, trained using the network from the Nature paper, which I think is the DQN paper. So you take the network that was used in the DQN paper, but you don't train it using DQN. You train it using policy optimization. And then what it seems to do is it takes about 10,000. You have to have a training set of about 10,000 environments or 10,000 levels before it actually is learning something that generalizes well to other environments from the same distribution. All right. Then in the right-hand plot, the authors of this paper showed that a different network actually does much, much better. We still see this kind of overfitting pattern where you need a lot of training levels to before it starts to generalize successfully. But the level that it's able to achieve is actually much, much higher. It's in the high 90s, whereas the convolutional neural net from the Nature paper is really leveling off in the 90s. Okay, so what's the point of this? The point of this is that we are actually starting to get good generalization, right? We're by training on enough variability, enough different levels, we actually start to see patterns of successful generalization happening. So that's great. All right, so we decided that we wanted to compare, we wanted to sort of replicate these results, but also include in the comparison DQN, which we think is going to generalize much less well. So we ended up switching to the level 2 difficulty levels only, and we tested on 10,000 levels from that set. DQN 20 million steps, PPO2 50 million steps. We used the same network from the Nature paper, which kind of peaked out at 90. And what we found, which I think is really interesting, is that DQN really was able to generalize. Right. So the more training levels that we used, the better DQN did at performing well on environments that are outside its training set. So that's good. It's not like DQN can't generalize. It just generalizes less well than the policy algorithm. And where we see that is at the level of where the dotted lines are. So the bottom dotted line is for the DQN algorithms on training and testing. The top dotted line is PPO on these level 2 environments, which is closer to 90% accuracy. Again, on the far right side of the plot. Once it has the 10,000 training environments that it can actually generalize from, yeah, DQN is able to generalize, just not as well as the policy-based approach. We did notice that prediction errors are associated with failure. Prediction error lower in training than testing. So trading equals testing given enough data, right? So again, it is able to generalize, like the environments that it hasn't seen before. It does about the same as the environments that it has seen before. Once it's seen enough environments, once it has enough data to actually kind of characterize the whole space of environments. I think that's all I want to say about that. All right, and then I think this is the summary side. I think this is like getting to the end of this talk, and we can kind of open it up to Q&A. So in summary, just seeing an algorithm, a reinforcement learning algorithm, perform well in an environment doesn't mean that it's actually mastering the task, right? It's the performance. I use the word seductive. Like, it looks really great and you can sort of convince yourself that it's great, but if you need to look closer, in many cases, the greatness is not true, right? We have to kind of do better science when we look at these things before we extrapolate and say, oh, this algorithm is really great. It actually is a master of this task. It may have just really memorized, and we need to kind of push a little harder. There's an analogy that you can make between reinforcement learning and supervised learning, but it's a little subtle, right? So I think a lot of times people focus in on the question of, well, there's lots of different states in reinforcement learning. And so that's kind of like lots of different training examples in supervised learning. But in fact, I think the more useful way of thinking about training examples in supervised learning is each training example in supervised learning corresponds to an entire environment in the reinforcement learning setting. So we're really kind of up a level compared to what the supervised learning people are doing. DQN really struggled to generalize in Amadar and CoinRun, and it did some, but weak generalization in the level 2 CoinRun difficulties that we ran. Or sorry, the level 2, the level 2 difficulty CoinRun experiments that we ran. Prediction error and internal representation distance actually turn out to be kind of good predictors of poor generalization. So you can tell when the network is in a scenario in which it's unlikely to generalize well, which is useful, right? It's helpful to know when the algorithm might be doing badly, instead of just running it and seeing that it's doing badly, right? It's good to be able to tell that in advance. We looked at adjusting training volume, model capacity, and exploration, and they all seem to help at least a bit. But in the future, it'd be really great to look at doing a flat out comparison with model-based reinforcement learning. So I think there's a real opportunity there, but it's hard to do deep model-based reinforcement learning. And I think that's one of the reasons we haven't seen a tremendous amount of progress there.